Video, we're going to take a look at the rational root theorem. Apologies in advance if there's any background noise. I'm at the library. Alright, so we're going to look at the rational root theorem, which I want to just be upfront with you. It gives you all, and I'll say all, and I'm going to really emphasize this, possible rational roots. Not to say that they are your actual answers, but I'm saying that these are just possible answers, not the actual answers. Okay, so basically you need to look through all the choices and decide if they work or decide if they don't work. If they don't work, move on and try to find something that does work. That's basically what the rational root theorem will allow you to do. And the way we do is we find the factors of your first term and divide it by the factors of your last term's coefficient. Sorry, I think I said that wrong. You want to find the factors of your last term, the constant, and then divide it by the factors of your first term's leading coefficient. Okay, so let me give you an example here. And what I'll do is I'll color coordinate this so you can make sense of what this is. So I'm going to show that this 2 is in red, and then this 2 is in blue, since those are my first and last terms. So what I do is I find all the possible roots by taking all the factors of the last term, which is in red, the 2, and those factors are 1, -1, and 2, -2. And I'm going to divide it by the factors on the leading coefficient, which is 2. So again, plus minus 1 and plus minus 2. Now I want to think of all possibilities. So what I'm going to do is I'm going to go in order, in sequential order, and I'll say let's do first 1 over 1. Well, 1 over 1 is 1, but I also have -1, right? Plus positive 1 over -1 is -1. -1 over +1 is -1. Positive 1 over +1 is +1. And -1 over -1 is +1. And so I don't want to repeat myself. I just say plus minus 1. I'm then going to go ahead and go in sequential order again and say now my next possibilities would be something like a 1 over 2. I could do positive 1 over -2 and I get -1/2. I can do -1 divided by positive 2 and still get -1/2. I can do positive 1 over positive 2 and get positive 1/2, or -1 over -2 and get positive 1/2 still. After I exhaust all possibilities of using my 1 in the top, now I'm going to look at all the 2's on the top. So I'm going to go 2 over 1, and so my possibilities are 2 over 1, 2 over -1, -2 over 1, and all the like. From there, I can then go ahead and do 2 over 2. Since 2 over 2 is the same thing as 1, I would just be repeating myself by doing 2 over 2. So I'm just going to leave it like that. What you'll notice is I have 6 total combinations of possible rational roots. And so I'll give you an example of how we can determine if a 0 is actually a value to this polynomial. What we're going to do is very similar to what we did last time. We're going to do synthetic division. We take all the factors of our polynomial. Make sure you consider every single term, that there's no missing blanks. If there was like no x squared in here, then you would simply say that this is 0x squared. Okay? And so you need to make sure you're writing all the coefficients of your polynomial. In this case, I have 2, -1, -7, 1, and 2. Again, if this -7 was like a 0, then I would have had to put 0 in here to make sure I account for the x squared. So I want to fill it in as a placeholder. Okay? But in this case, I'll just put -7. Alright, so these are our possible roots. And so what we can do is actually just go in, if you want to go in order or just randomly pick one. What I recommend, my tip for you, is when it comes to finding possible rational roots, you should always try the values of 1 or -1 first. And the reason being is because if you think about factors of numbers, every number will always have 1 that it can multiply by or divide by, because you just always get the same number. So that's always a great option when checking to see if there's a 0. So let me go ahead and try that. I'm going to try 1 out. And so if I divide by 1, let's see what happens. I get 2 here, 2, 1, 1, -6, -6, -5, and -5. Oh no, look, I actually get a remainder of -3. because I got a remainder, keep in mind that this is telling us that this is not a factor. So it turns out that 1 was not an actual possible root. When it doesn't work, you just move on and try another one. Let's try another one, okay? Let's try, I don't know, let's just try 2. Since we've already tried 1, let's just try 2 now. I could try -1. Let me actually try -1 as well. So I'll do it again. 2, -1, -7, 1, and 2. And again, we'll do it again. 2, -2, -3, 3, -4, 4, 5, and -5. Oh, look, we still get -3. So this one doesn't work either. So 1 and -1 both don't work. You'll notice I am running out of space here. I'm hoping that you do see that 1 and -1 don't work. So what I'm going to do is I'm just going to erase it because I'm running out of space, and that way I have more room for testing again. So this time, let's go ahead and try a different number. So 1 and -1 both don't work. I'm going to go ahead and try another one now. Okay, so let's go ahead and try, let's try 2. Okay, so we're going to bring the 2 down. 4, 3, 6, -1, 2, 3 times 2 is 6, and we get 8. Okay, so that one didn't work either. Alright, so let's try another one. Oh wait, oops, I think I did that wrong. Hold on, let me double check this again. When I multiply 2 times -1, I was supposed to get -2. And we get -1. Oh, it does work. Never mind. I'm sorry. It does work. So we see that 2 actually is a 0. Okay, so if 2 is a 0, we can now see that, again, as I told you before, since this is x to the 4th and we're divided by x, this becomes a 2x cubed plus 3x squared minus x minus 1. And so this polynomial, what we did was we basically were able to take out the factor of x minus 2. And so what we want to do is just keep repeating this process until we can actually find all the broken down zeros. We just keep breaking this up. Okay, so let's go ahead and do that again. Let's go ahead and try another one. Let's try -1/2. And this time, because I've already divided my polynomial, I'm going to use the coefficients of 2, 3, -1, and -1 here. And I'm just going to repeat this process. So I'm going to bring the 2 down. I multiply and I get -1. We add, we get 2. Multiply, we get -1. We add, we get -2. Multiply, and we actually get +1. Oh look, we actually get 0 again. So it turns out that -1/2 is also a factor. I'm going to go ahead and write it over here. We remember that we first divided by x minus 2. That's a factor. Now we have a new factor. It was x minus 1/2. And now our new polynomial becomes, look at those 2's. So we have 2x squared plus 2x minus 2, like that. And so this becomes our new function here. Actually, if you notice that these all have 2's, I can actually factor the 2 out from all of them. So let's see what we get. 2 times x minus 2, x minus 1/2, times x squared plus x minus 1. So I just factored the 2 out from that trinomial there. Alright, oops. That trinomial, you cannot factor that, so I think this is pretty much as far as we can go. This is telling us that our real zeros, the zeros that actually work here, are basically the values of 2 and 1/2. Those are our rational roots, basically. Okay? Alright, so that'll do it for problem number, or I guess there's no example number here. Okay. Alright, let's take a look at number 3. So you can basically just reapply this technique. Now, one thing I will say is that the rational root theorem, if you think about how you use certain tools, and I'll just kind of write it over here. If you recall, when you solve quadratics, we know that there's a method called factoring that allows you to solve quadratics easy or easier, but sometimes it doesn't always work, right? Always work. However, if you want something that always works, you could think about the quadratic formula, and the beauty of this is that it always works. The problem with this method is that it could be kind of tedious, long, right? So These can often be troublesome just in terms of the arithmetic, and factoring is a lot easier, but it doesn't always work. So similarly, when we're solving a polynomial function, it works the same way. When you work with polynomials, think of all the tools at your disposal and think about what method you want to use. Sometimes we could factor. Again, it's easier, but doesn't always work. Not 100% effective, right? However, the method that we have been learning about, this whole idea of using the rational root theorem, it's a great method because it actually always works. It will always be able to give you your rational roots. However, what again we see is that sometimes it can be tedious, it can be long, it's just a little troublesome. So basically what I'm trying to tell you here is when we are finding real zeros of polynomials, I want you to think of all your tools at your disposal and just use what's best, okay? So I'm going to go ahead and erase this now, and let's take a look now at our next example. So again, think about as we solve for the real zeros, what do you want to do with this? We could do rational root theorem, right? We could say let's try all the values of 2 over plus minus 1 and think of all those possibilities, right? Plus minus 2, plus minus 1. You'd have to test all of them. You could do that. It could be fairly lengthy, but if you think about it, you do have 4 terms, and you could also factor by grouping. So if I try factor by grouping, I'm going to factor x squared out from the first 2 terms, and we're going to get x plus 2. From the last 2 terms, I'm going to factor out -1, and we get x plus 2. So you can see here that x plus 2 is something that they both have in common. We can factor out the x plus 2 and be left with x squared minus 1. So therefore, this function is equal to x plus 2. Since x squared minus 1 is the difference of squares, that's the same thing as x minus 1 times x plus 1. And the beauty of that is you know your zeros now, -2, 1, and -1. It makes it nice and easy, just like that. So you can see here, we didn't need the rational root theorem on this one. If you can find a method of factoring, then all the more power to you.